Hello viewers, friction question 2. A textbook of mass 2 kilograms is dragged across a table. The static coefficient of friction between the book and table is μs equals 0.2. Now, what minimum force is required to move the book if the force is applied horizontally? So the force required is force due to friction is the coefficient of friction times the normal force. Coefficient of friction we're given to be 0.2 multiplied by the normal force. The book is 2 kilograms multiplied by 9.81, and if we calculate that we get 3.92 newtons. Okay, now would you expect the minimum applied force to increase or decrease if it was applied upwards at an angle of 8 degrees to the horizontal? Explain why. You may wish to draw a free body diagram as part of your answer. Assume the book is still in contact with the table. Okay, so let's draw our free body diagram, and notice now that since we've got an upwards component to the force, let's look at what's happening in the vertical direction. So downwards we've still got the weight force, mass times gravity. Upwards we've got the normal force from the ground or from the surface of the table, and we've also got now an upwards component of the force that you're applying here. So if it's in vertical equilibrium, which it needs to since there's no acceleration in the vertical direction, that means that 0 needs to be equal to n plus a, the two upwards forces, if we're taking upwards to be the positive direction, minus w. Let's solve that for the normal force. So the normal force is going to be the weight force minus the applied force. So since we've got an upwards applied force, the normal force is going to be less, and that's because the applied force is reducing the amount that the table needs to do in order to support the weight of the textbook. So we're saying that the normal force is going to be smaller, and therefore, so Fn is smaller, and therefore we're expecting the friction force, which is a constant times the normal force, is going to be smaller as well. Because if Fn gets smaller, then Ff is going to get smaller as well for the same coefficient of friction. Now part C, we need to prove it, so we need to actually do the calculation. So let's draw the proper free body diagram of the textbook, and let's say that, so we've got a weight force, we've got a normal force, so we're pulling it upwards at an angle 8 degrees above the horizontal, and let's say that that is going to be A for the applied force, and we've got a force due to friction which is backwards. Okay, so let's draw up our force table. So this is like what we were doing in the vector section. We've got forces, we've got a horizontal component, and we've got a vertical component. Let's start with the normal force, and the horizontal component is 0 because this is exactly upwards. We know that it's upwards, so therefore the vertical component is positive. We don't know its size, so let's just call that n for now. So for the applied force, so a horizontal component is, if we look at this right triangle, it's applied to the right, which means it's going to be positive, and this is going to be A is your hypotenuse, this is the size of the force. We're finding the adjacent side, so this will be cosine of angle is 8 degrees, and vertically we also have A, but this is now going to be opposite side, so we've got sine of 8 degrees. So the weight force, and this we already know, it's got a horizontal component of 0, and this vertical force is going to be negative because it's downwards, and its weight force is mass times gravity. 2 times 9.81 makes that 19.62. Now we have a force due to friction, which is to the left, which is mu times Fn. It's left, which means it's negative. Now mu times Fn, mu we know, which is 0.2 is our coefficient of friction, times the normal force, which all we know so far is that it's n. We don't know a value of it. And the whole thing's in equilibrium because we're looking at when it's on the verge of moving. It's not starting to move yet, so it's still in equilibrium. So the totals must therefore be 0. So 0 for both columns. And now we need to work out our two equations. So from the FH column, we've got a cos of 8 degrees minus 0.2 times the normal force equals 0. And from the vertical column, from FV, we've got n plus a times the sine of 8 minus 19.62 equals 0. So therefore we can solve that for the normal force. So the normal force is 19.62 minus a sine of 8 degrees. Okay, so we're going to now substitute that into the FH equation. And if we do that, we get a times cosine of 8 degrees minus 0.2 multiplied by 19.62 minus a sine 8 equals 0. And let's multiply that 0.2 into the bracket, so therefore we get a times cosine of 8 minus 0.2 times 19.62 is 3.924. Then we've got minus times minus, so we've got a plus 0.2 a sine of 8 equals 0. So let's move that 3.924 to the other side of the equation. And everything else that's left on this side has a common factor of a. So we've got a multiplied by, we've got cosine of 8 degrees. That we've dealt with by moving it to the other side. The 0.2, so we're taking out a as a common factor, so we've got 0.2 times sine 8. Okay, so we've got a times something equals 3.924, so therefore a is 3.924 divided by cos of 8 degrees plus 0.2 times sine of 8 degrees, and if we calculate that, we get 3.85 newtons. So, as we predicted, the force due to friction required to move it reduced from 3.92 newtons down to 3.85 newtons. So it did go down by exerting a slight upwards force rather than just a horizontal force. So we're able to get the book moving a little bit easier there. Okay, thanks for watching. Over and out.